Welcome, brothers. Today I'm bringing you a highly practical explainer on exactly how to diagnose and mitigate thermal shock before it completely wrecks your plant. Look, if you're a wastewater operator or a plant manager, you already know that temperature is the silent killer of our biological systems. It's an invisible stressor, often totally ignored until the damage is already done and the alarms are screaming. So today, we're going to equip you with the knowledge to stop it dead in its tracks.
Here's the battle plan for today's shift. We'll cover the thermal shock threat, spotting the warning signs, pinpointing the heat source, some scenario-based action plans, and finally, your emergency operations checklist.
Section 1. The thermal shock threat.
Okay, so what actually happens when your influent temperatures spike above 35 to 38 degrees Celsius, or worse, approach 40 degrees? Well, two catastrophic things happen at the exact same time. First, it absolutely tanks the dissolved oxygen saturation in your aeration basins. You could literally be running your blowers at absolute maximum capacity, pushing all the air you have, and you still won't hit your target DO. Second, this extreme heat fundamentally changes the hydrodynamics and the viscosity of your water, and that completely disrupts the settling process in your secondary clarifiers.
And you know, it's not just the physics at play here, it's the biology. Our hardworking mesophilic bacteria, the very bugs we rely on day in and day out to clean the water, get severely inhibited by this heat stress. This leads to a massive, rapid drop in COD and BOD removal, and your nitrification process, it practically grinds to a halt. In extreme cases, you might even trigger unwanted thermophilic bacteria or accelerate anaerobic decomposition in the clarifier, which brings on that terrible, rotten odor nobody wants to deal with.
Section 2. Spotting the warning signs.
So how do we catch it early? Take a sample straight back to the lab and check your sludge under the microscope. Thermal stress causes the activated sludge to form loose, pinpoint flock. You'll actually see your 30-minute settling volume, your SV30, drop. But paradoxically, the clear water on top will remain extremely turbid because of all those tiny, broken flocks floating around. You might also notice a thin, creamy white or gray foam developing right on top of your aeration tanks.
Now, this formula perfectly illustrates the core of the problem, dissolved oxygen saturation. You don't need to memorize the math, but you do need to know the reality of it. As the temperature rises, the maximum oxygen your water can physically hold drops drastically. To put that into perspective, at 20 degrees Celsius, your water can hold about 8.8 milligrams per liter. But push that temperature up to 40 degrees, it drops to just 5.6 milligrams per liter. That means your DO is going to fall dangerously low, and it's not because your biological load spiked, it's strictly because the water's too hot to hold the air.
And a quick pro tip, when DO drops suddenly, always double-check your sensors. High heat can cause serious temperature compensation errors on both your DO and pH meters out in the field. Don't just blindly trust the SCADA screen when a heat wave hits. Get out there and verify it with a recently calibrated handheld meter.
Section 3. Pinpointing the heat source.
Once you confirm you've got a heat problem, it's time to play detective. Start by getting out there and continuously measuring temperatures at the influent channel, your equalization tank, and your aeration basins. You really need to be using electronic thermometers with data logging capabilities to truly track the heat profile of your plant over time. You can't fix what you aren't tracking.
The key here is knowing exactly where to look based on your specific industry. If you're working in food and beverage, you need to watch out for hot CIP washing cycles dumping 50 to 80 degree water down the drain. In the power or paper industries, boiler condensate can push a blistering 90 degrees. Heck, even basic cooling tower bypasses and chemical plants can easily hit 50 degrees. Identifying your most likely culprit is half the battle.
To actually catch them in the act, you've got to cross-reference your production logbooks and use your auto-samplers alongside your lab meters. This is how you pinpoint the exact minute those hot discharges are hitting your headworks. You want to correlate those heat spikes with specific production schedules, like, say, a scheduled tank sterilization.
Section 4. Scenario-based action plans.
All right, let's talk solutions. Scenario A is a sudden, hot production discharge. Your urgent action here is to immediately cut or reduce that hot flow and dilute it with cold water or even filtered effluent if you have to. Max out your blowers right away to compensate for that DO drop. In the short term, you've got to work with production to adjust their discharge schedules, but long term, you absolutely must install interlocked online temperature sensors to automatically divert that flow before it ever hits your bugs.
Honestly, installing proper, dedicated cooling towers and comprehensive bypass piping is your absolute best long-term defense against those unpredictable, scorching industrial dumps. If your plant handles high-temp industrial waste on a regular basis, a heat exchanger isn't a luxury, brothers. It is a fundamental requirement to keep your plant alive.
Now, scenario B is extreme summer heat, which is brutal if you operate in a tropical zone. If the summer sun is literally baking your open tanks, step 1 is deploying emergency surface misting and temporary reflective tarps. After that, bring in large industrial fans for forced evaporation and heat exchange. Eventually, though, you need to budget for physical sunshades or greenhouse covers to block that direct solar radiation for good.
Scenario C is a nightmare. Your primary cooling system fails. When this happens, immediately switch to your backup misting systems or start pouring cold water straight into your EQ tank. You must reduce the plant load if at all possible. Then, get your maintenance crew out there ASAP to clean the tower's lamella, clear the nozzles, and check the fans.
And to prevent these cooling failures from sneaking up on you in the first place, your heat exchangers and lift station pumps require a highly strict preventative maintenance schedule. And listen, this must be based on actual run hours, not just some random dates circled on a calendar. Keep those systems in absolute peak condition, because when a heat wave hits, you're going to need every single ounce of cooling capacity they have.
Scenario D is dealing with an equalization tank that is just too small to buffer the heat. It happens a lot. Urgently, you'll have to dilute with groundwater or effluent. Short-term, you need to demand the production paces their discharges evenly over a full 24-hour cycle. Don't let them dump it all at once. Long-term, you need to bite the bullet and physically expand that tank to achieve a proper 8 to 12-hour retention time.
Never forget this core principle of plant design. Upgrading to a large equalization tank, sometimes even an enclosed or domed one, serves as your plant's absolute best thermal shield. A big EQ tank mixes those intermittent hot dumps with cooler background flows, completely neutralizing the threat before it ever reaches your sensitive biological basins.
Section 5. Emergency Operations Checklist.
When the heat hits your plant, do not panic. Take a breath and immediately check your logbooks. Run your emergency lab checks. Analyze the mixed liquor suspended solids, your MLSS, using your respirometers. And keep your eyes totally glued to your SCADA system trends so you can see exactly how fast the temperature is rising and how fast your DO is falling. I want you to systematically run down this 10-point checklist. Measure your headworks temperatures. Calculate your new DO saturation limit. Inspect your cooling systems. Check your 30-minute settling volume for that pinpoint flock we talked about. Compare your current MLS right now to your baseline. Turn on your backup blowers to push maximum air, and finally, and this is crucial, physically demand that the production facilities stop their hot discharges until your plant stabilizes. You are the last line of defense.
We know a large equalization tank is vital, and we know our bugs simply cannot survive above 40 degrees. But I want to leave you with this final, absolutely critical question. Are your plant's thermal sensors properly interlocked to automatically divert boiling water before it kills your plant? Think about it, check your systems today, and keep those bugs happy. Thanks for joining me on this Explainer, brothers, and I'll see you on the next shift.